when the components of the vectors to be added are given, such that the vectors may be represented, for example, in 3 dimensions in terms of I hat, j hat, and k hat. Like here, the two vectors A, which is represented by ax I hat plus ay j hat plus az k hat, and B equals bx I hat plus by j hat plus bz k hat. To add such vectors together, what we do actually, we take the coefficient of I hat here, which represent the x components of the vector, and add them together. Here we get the x component of the sum or the resultant Rx. Of course, this accompanies with, supposed to be accompanied with I hat. Similarly, add the coefficient of j hat, which represent the y component of the vectors, then you get the x or the y component of the resultant. Of course, this must be accompanied with j hat. In the same manner, the coefficients of k hat, which represent the z components, can be added, and this gives the z component of the resultant. Again, the x component must be accompanied with I hat, and the y component with j hat, and z component with k hat. Those three represent the component vectors. When added together, they give us the resultant or the sum of those given vectors. This is an example, addition of vectors in 3 dimensions. Given two displacements, d equals 6 I hat plus 3 j hat minus k hat meters, and the second displacement called e equals 4 I hat minus 5 j hat plus 8 k hat meters. Find the magnitude of the displacement 2d minus e. To find the addition of these vectors, let's call 2d minus e equals f. So our target is to get the magnitude of this f. To do that, let us substitute d in here into our equation here, and then also substitute e into here. Then we'll get this. Now, in this vector equation, we will have the I coefficients, the I hat coefficients must be added, as these coefficients represent the components of the vectors. Then what we get from here, 12 minus 4 for I hat. For j hat, we add 6 plus 5. So we get 6 plus 5 in here. And finally, for k hat, we have minus 2 minus 8 k hat for k hat. Then what we have, 8 I hat plus 11 j hat minus 10 k hat. Now, how can we get the magnitude of this final vector? We just apply the Pythagorean theorem by squaring the x component of the vector f, and also squaring the y component of the vector, and then finally the square of the z component of this vector, and add these squares together and take the square root. Here we are, and we get an answer of 17 meters for the magnitude of the final vector. This is an application for addition of vectors in 2 dimensions. In this problem, consider two vectors, a equals 3 I hat minus 2 j hat, and b equals minus I hat minus 4j hat. Calculate part A, the addition of these two vectors, A plus B. In part B, calculate A minus B. Well, in part C, determine the magnitude of the adding vectors A plus B. In part D, determine the magnitude of A minus B. And finally, in part E, find the directions of A plus B and then A minus B. To do that, instead of following the addition of vectors by drawing them, we can do this addition of vectors in the equation right away. So here, let's first start with the coefficients of I hat, and then those coefficients which represent the components of the x components of the vectors, then add them together. Here we have 3 minus 1, we'll get 2 for I hat. For j hat, we'll do the same thing. For j hat, we have the components, the y components of the vectors can be also added together. Here minus 2, minus 4, that is 6 minus 6j hat. So the added vectors give us 2i hat minus 6j hat. We'll follow the same procedures in the subtraction of these vectors. Here we get a minus b, replacing the positive sign in part A by a negative sign. And then take first the coefficient of I hat. The coefficients of I hat to be added are 3 plus 1, and then we get 4. And for the j hat, also we're going to add the y components here, minus 2 plus 4, that is 2j hat. And here the vector is 4i hat plus 2j hat. Actually, the first vector is expected to be in the fourth quadrant as long as the x component is positive while the y component is negative. However, for the second vector here, the two components are positive, and this vector is expected to be in the first quadrant. To do the magnitude, all what you need to do, you just take the x component here and the y component here, take the square of each one and then add them together and take the square root to get an answer of 6.32 for the magnitude of the added vectors. The magnitude of a minus b can be done in a similar way. Take the component of this vector, which is 4, and that of the y component as well. Then take the square of these components and add them together. Take the square root, you will get an answer of 4.47 for that. Regarding the directions, for the added vectors, take the y component, the tan inverse of y component divided by that of the x component. And here we get an angle of 288.4, and this angle obviously in the fourth quadrant. For the direction of the subtracted vectors, again, take the tan inverse and take the y component and divide that by the x component. The tan inverse of this divided numbers give us 26.5 degrees, and that is in the first quadrant and as expected. Here the students must do this exercise on the addition of vectors. Here we have two vectors A and B are precisely equal magnitudes. For the magnitude A plus B to be 100 times larger than the magnitude of A minus B, what must be the angle between them. This is another application on the addition of vectors in 2 dimensions. And this problem's taking on part A, taking a vector equals 6i hat minus 8j hat units, and b vector minus 8i hat plus 3j hat units, and that of vector C equals 26i hat plus 19j hat. You are asked to determine the unknowns small a and small b such that the product of small a by the vector A added to that of small b multiplied by vector B plus C equals 0. Part B, a student has learned that a single equation cannot be solved to determine values for more than one unknown in it. How would you explain to him that both A and B can be determined from the single equation used in part A? The solution to this problem is as follows. Now, as long as the 3 vectors A, B, and C are in the xy plane, then one can easily substitute them into the vector equation here. And then we'll get equation 1 as follows. Obviously, this vector equation having 2 unknowns can be separated into 2 algebraic equations. One equation along the x-axis and the other along the y-axis. The algebraic equation for the components along the x-axis can be obtained by taking the coefficients of I hat on both sides of the vector equation 1. And here we are. For the y-axis equation, taking the coefficients of j hat and equate both sides of the vector equation, we'll get the other algebraic equation. Then, if you want to solve these two equations simultaneously, in order to find A and B, all what you do, you multiply equation 2 by 4, and then multiply equation 3 by 3, and then you will get equation 4, that's obtained from equation 2, and then equation 5 obtained from equation 3 after the multiplication process. Now we have these 2 latter equations, add them together, one may get this answer for B. Then substitute this B back in one of the above equations, especially in equation 2, to get an answer for A equal 5 units. And here we are, and the problem of part A is solved. Well, regarding part B of the problem, how can we get 2 unknowns A and B from a single vector equation? Well, the answer is this vector equation is actually divided in 2 algebraic equations, and this allows us to determine the 2 unknowns by solving the 2 algebraic equations simultaneously, as we have just seen in part A. The question, what about if we have 3 unknowns in a state of 2? In this case, we need vectors represented in 3 dimensions and expressed of the 3 unit vectors I hat, j hat, and k hat in order to get the 3 unknowns from 3 algebraic equations. The following is an exercise on the addition of vectors in 2 dimensions. Well, in this exercise, vector A has x and y components of minus 8.7 centimeter and 15 centimeter respectively, while vector B has 13.2 centimeter for the x component and minus 6.6 centimeter for the y component. If the vector equation is given as a minus b plus 3c equals 0. What are the components of c? Well, we'll give a clue to the students in order to go forward and solve this problem. Write the vector a in terms of its component represented by I hat and j hat. Similarly, for the vector b, write the vector b in terms of I hat and j hat by substituting the components into the vector equation, and then follow this equation on the addition of vectors, and you'll get an answer for C right away, where the x component is going to be 7.3 centimeter and the y component is minus 7.2 centimeter.